Hello and welcome to the solution for problem of the day, posted 7/6, which I believe was yesterday. Okay, here it is. Prove that the tensor equation for the gradient is given as this. Okay, here's what we had to work with. So we had the covariant derivative, which we like, and a covector basis, which we don't want, or we had a contravariant derivative, whatever that is, with a vector basis. So the problem was put this with this. How do you do that? Well, where does that come from? That comes from this, using the metric tensor to raise an index. So this j gets absorbed and I slides over and we get this. So we can put this right back in there and we get this expression. Now all we got to do is figure out what this is. What is the covariant derivative of a scalar field? Well, we'll expand it like we always do. The first term is always the partial of whatever it is with respect to the coordinate. This happens to be j. Then we add our connection for how many indices we have. We don't have any indices. This is a tensor rank 0, so there's no connection. So this just goes right back in here, and we got the proof. That's how easy it was. Okay? Part B. Given the basis vectors in spherical coordinates, these three, using the derived equation from part A to find the gradient in spherical coordinates. Okay, so we take our generalized equation, which is that. I said the basis vectors are orthogonal. Now, what's that mean? That means we only need to find these components, the diagonals of the metric tensor, because all the off diagonals are 0. When it's orthogonal, that's what happens, right? So as an example, g theta is 0, g phi is a 0, etc. Okay, so all we got to do is square ER, we get 1. We square E theta, we get R squared. We square G phi, E phi, and we get R squared sine squared the theta. Okay, now we need the inverse metric tensor. Well, that's easy because the off diagonals are all 0, right? So we just put all this under 1. So now we have the 3 components that we need to solve this equation. So here's the generalized equation. Okay, so this is a double sum, right? You got I, j, j. So, but it can only be what we have. Everything else is 0. So we just start with RR. What is GRR? It's 1. Then we write down the partial of L with respect to R. ER. What's G theta theta? Oh, here. We need to go down to here. I'm sorry. Okay, so we got 1, the partial of L with respect to R, ER. Then we're going to have plus G theta theta, which is 1 over R squared. This term plus G phi, which is 1 over R squared sine squared theta, partial F respect to phi E phi. So this is the equation for the gradient in spherical coordinates. And you say, hold on a minute there, dog. This is not what we used in vector calculus. The reason is because they make these unit vectors, right? So you divide the vector by its magnitude, you get unit vectors. And using unit vectors is not a proper tensor equation. So we just stop here. Okay, that was it. I'll see you later.